Hi, now let us pass through a problem based on reciprocity theorem. Verify the reciprocity theorem for the network shown in figure. Okay, here we have a 20-volt voltage sources and some resistances are given. It is required to verify the reciprocity theorem. Okay, right. Let us try to solve the question. In order to prove the reciprocity theorem, we need to know the statement of a reciprocity theorem, or otherwise, what we have to do in a reciprocity theorem. Okay, for that purpose, we should have a network and a single voltage source. We have to find the current in the last branch. Okay, right. Let us denote it as I. Then we have to transform the we have to shift the voltage source from node A dash into BB dash, like that. This is a network given. Here it is BB dash. Next, we have to disconnect the voltage source from the node A dash and we have to connect it into the terminal BB dash. Then evaluate the current in the node A dash. Okay, what should be I. Then in both cases the ratio between V and I will be same. That is what the reciprocity theorem says. Okay, right. Now let us prove that. Just compare this block diagram with our given network. Here we have a 20 voltage source. Okay, in this network also there. So what we have to do is you have to find the current in the outer branch. So we have to find the current through the 2 ohm resistance, this 2 ohm resistance. Okay, for that purpose I'm going to redraw this network completely once again. So in order to prove the concept, if we look if we take a look at this block diagram, we have to evaluate the current through this network. Let us mark these points as A dash and this one be B dash. So let's find the current in the branch B dash. Okay, right, that is the first step. Let's denote it as I. Then we have to take the ratio between voltage and current, V by I or I by V, whatever it may be, doesn't matter. So let us evaluate this current. We can use any methods in order to find the currents, in order to find the current through the this 2 ohm resistance, because there are many ways, many theorems to apply. Either you can find the current through this branch using Thevenin's theorem, Norton's theorem, then simply by using nodal analysis, or the most simplest method, that is use the current division rule. That is the simplest method among them. So let us try to solve for this current I through the current division rule. Doesn't matter whatever it may be, you are getting this same answer. Okay, right. Now let's find the current using simply the current division rule. Okay, right. In order to find the current through this branch using current division rule, we have to we should know what is the total current supplied by this voltage source in this circuit. Okay, so let us mark it as IT. IT is the total current provided by the 20 volt voltage source. Okay, then how do we find that? Simply by Ohm's law, we know that V is equal to I into R. Then current will be the ratio between potential difference and the total resistance. Potential difference in this case, the potential difference V is equal to 20 volt. Then in our case, what about this R? R will be the equivalent resistance feeling at A dash. So You have to find the equivalent resistance at A dash, then take the ratio V by R equivalent. Then we will get the total current supplied by this voltage source. Let it be IT. So for that purpose, I'm going to find the total resistance across this point A dash. Now, so now we are going to find the equivalent resistance across A dash. So let us try to solve the resistance from the other end, from this end onwards. What about the relationship between these two resistors, these two ohm resistors? If we look at them, we can say that both these two resistances are connected parallel to each other. Then equivalent resistance will be R equivalent resistance. These two are parallel to each other. Okay, so let us replace these two resistances using their equivalent resistance. Okay, let us let us draw that circuit. Okay, here I'm going to replace the equivalent using the equivalent resistance of these two ohm resistances. This is, sorry, this resistance is equal to 2 ohm parallel 2 ohm. Okay, right. If 2 ohm resistances are connected in parallel to each other, then equivalent resistance will be 2 into 2 divided by 2 plus 2. So that will be 1 ohm. Okay, right. We replaced these two resistances using their equivalent resistance. That is 2 ohm parallel 2 ohm. So 2 into 2 divided by 2 plus 2 gives 1 ohm as answer. Now, what is the relationship between these 2 ohm resistance and 1 ohm resistance? They are in series to each other. Okay, so let us replace these two resistances, this 2 ohm resistance and 1 ohm resistance using their equivalent resistance. Okay, right. Okay, 2 ohm and 1 ohm resistances are series to each other. Then equivalent resistance will be 2 plus 1. That 2 ohm series to 1 ohm, that gives 3 ohm as equivalent resistance. Okay, right. Now what about these 3 ohm resistance and these 3 ohm resistance? They are parallel to each other. So again, let us replace these two resistance using their equivalent circuit. Okay. Okay, these 3 ohm and 3 ohm are parallel. Okay, let us replace it with their equivalent resistances. 3 into 3 divided by 3 plus 3. That will give this resistance as 1.5 ohm. Okay, right. Now what about the relationship between these 2 ohm and 1.5? They are in series. So R equivalent will be, this is A and this is A dash, this is R equivalent. R equivalent will be 2 ohm in series with 1.5 ohm, gives 3.5 ohm. Okay, so R equivalent will be 3.5. Now let us find the total current. Now let us find the total current IT. Okay, IT total current, that will be equal to voltage potential difference divided by R equivalent. Okay, right. Now let us find the total current supplied by the voltage source. That will be current IT is equal to V by R equivalent. What about the voltage magnitude of this voltage source? That is equal to 20 divided by R equivalent. R equivalent we obtained it as 3.5. Okay, 3.5. That will be the total current supplied. That is going to be 5.71 ohms. Okay, now let us apply the current division rule. This is 5.71 ohm, no, sorry, ampere. Sorry, I have made a mistake here. That is current, so the result should be in ampere. This is I total. and a portion of this IT will split at this node, and a portion will flow through this 3 ohm resistance, and the remaining current will flow through this direction. Okay, then again upon reaching this node, the current will again split into two components, and a portion will flow through this through 2 ohm resistance, and that will be the required current I. Okay, right. So we have to evaluate these two currents first. In order to find this current, we should know the current coming at this node. Okay, right. So let us mark it as I1, and let this one be I2. Okay, I2 upon reaching here, I split into two I, and the next is I3. Okay, right. Now we how to find I2 in order to find I. How can we find I2? Again, we have to let us apply the current division rule. In order to find the current I2, I am going to replace these 2 ohm resistances with their equivalent circuit and going to redraw them. Okay, right. Okay, I'm going to replace these two resistances with the corresponding equivalent resistance. Then the resultant circuit will be, try to compare with the circuit. Okay, here we have to find I2. Here we have A dash, then total current IT, that is the current flowing through the 2 ohm resistance. So let us mark here as 2 ohm, and magnitude of IT we obtained is 5.71. So let us write that 5.71. Okay, reach of the node here, and is split into two subcomponents I1 and I2. Let us mark here also I1 and I2, and then 2 ohm resistance. Here 2 ohm resistance is drawn. This is the node from which the current is again splitting into two. Okay, so first of all I am going to find I2. For that purpose I am going to replace these two resistances with their equivalent resistance. These 2 ohm and 2 ohm are parallel, so let us replace that resistance with their equivalent. 2 ohm parallel 2 ohm, that will be 2 into 2 divided by 2 plus 2 gives 1 ohm. Okay, now let's apply the current division rule. And the current, I'm going to discuss deeply about the current division rule, because our role is to prove the reciprocity theorem. So I will give the description for the current division in the description box. Okay, try to find the current division rule in my previous video, and the link will be available in the description box. Okay, now I'm going to apply the current division rule to find the branch current I2. What is the purpose of finding I2? If we know the current I2, then only we can find the current I, that is the required current for the reciprocity theorem. Okay, right. So I'm going to find the branch current I2. I2 will be the total current IT into, okay, total current IT. IT is 5.71 ampere. Okay, this is IT into opposite resistance. I2 is the current flowing through this 2 ohm resistance. So opposite resistance means 3 ohm divided by total resistance in this loop. Okay, that is this 3 plus 2 plus this 1. Okay, that will be the magnitude of current I2. Then what about I total current? That is 5.71 into 3 divided by 6. The answer is I2 is equal to 2.86 ampere. This is 2.86 ampere. means in this figure I2 we are getting is 2.86. Okay, this 2.86 again reaches the node here, and that is splitting into two, I and I3. Again we have to find I. To evaluate the current I am going to consider this circuit only, because the resultant current that reaches the node here, we obtained that its magnitude is equal to 2.86. So we have to find the branch current I from this from this current 2.86 only. So let us redraw this circuit only to find I, and thereby we can apply the current division rule again. Okay, I have read on this circuit. This is 2.86 ampere current, then this node, and this is I3, 2 ohm resistance, and again this is 2 ohm resistance, and I. Here the total current is 2.86. Okay, let us find I by using current division rule. Total current 2.86 into I. Okay, then the resistance opposite to this branch, that is this 2 ohm resistance, divided by total resistance in this loop, that is 2 ohm plus 2 ohm. This is current division rule, and I am going to discuss current division rule here. That is described in my one of my previous video, and please go through that. And here what we are getting is 2.86 into 2 divided by 4, and the result will be 1.43 ampere. So the output current is the current flowing through the outer branch BB dash, and the result we are getting is 1.46 ampere. Okay, now we have the input voltage source 20 volt voltage source, and output current 1.46. Now let's take the ratio between V and I. That is the statement of our reciprocity theorem. So let us take the ratio. Here I'm going to take the ratio between the excitation or input and the output, or the response, input to output ratio. That is input here is voltage, that is 20 volt voltage source, and output here we are obtaining is current. So let's take the V to I ratio, 20 divided by 1.43, that is 13.99. Okay, now let us mark this equation as equation number 1. Now this is our case 1 study, that is over. Okay, now this is case 1. Now let us pass through the case 2, in which we have to disconnect this 20 volt voltage source and put it here and observe the current. Same concept, just disconnect the voltage source, then connect it in the output terminal, then observe the current at the input terminal AA dash. I'm going to redraw the circuit again. Okay, now in case 2, I'm going to disconnect this 20 volt voltage source, and that was connected across AA dash. Now I'm going to put in the terminal BB dash. Here we have a resistance, and I'm going to connect it after that. This is 20 volt voltage source connected across B dash. Then I have to find the current flowing through terminal AA dash. I am going to mark it as I. Okay, right, this is the equivalent circuit for the case 2. Okay, okay, right. Now we had to find the current I, means the current flowing through the outer 2 ohm resistance. That will be same here also. Let us proceed as in the same manner. Let us solve for I using current division rule. For that purpose, again I have to evaluate the total current IT. Then let us assume that the I1 be the current flowing through 2 ohm resistance, and here it is I2. Okay, I2 again reaches this node and splitting into current I and I3. So first of all we have to find the total current IT supplied by this 220-volt voltage source. Okay, and now let us find the total current IT. IT will be equal to volt. Simply current is equal to V by R. So IT will be 20-volt voltage source divided by the resistance feeling across this point. Means resistance, total resistance across the voltage source. Means total resistance across here and here. That is total resistance across CB dash, that is equal to V divided by RCB dash. Okay, right. Total resistance feeling at across the node CB dash, RCB dash. That is R. Let us denote it as R equivalent. Now let us find the R equivalent. So for that purpose, I'm going to redraw the circuit. Okay, now here A and A dash, A and A dash, then 2 ohm resistance, then up to BB dash. Let us, we can draw. Then across B and C, we have resistance of 2 ohm. I'm drawing those that resistance as B and C horizontally here. Okay, finally this one will be the lower terminal. B dash. Okay, right. Now we have to evaluate the equivalent resistance across CB dash. CB dash. Okay, C and B dash. So for that purpose, let us solve the resistance from the opposite end. From here, we can find the equivalent resistance. These 2 ohm and 3 ohm are parallel to each other. So let us redraw the circuit using a single resistance. Here 2 ohm parallel 3 ohm, then followed by this 2 ohm resistance, then 2 ohm resistance. Okay, then this is terminal B. After that 2 ohm resistance, then C, B dash. Okay, here R equivalent. Okay, what about this? Is 2 ohm resistance. This 2 ohm and the equivalent of 2 ohm and 3 ohm resistance, that is 1.2 ohm. Okay, this 1.2 ohm and this 2 ohm are in series. Okay, so let us redraw these two resistance by its equivalent resistance, 2 ohm plus 1 ohm. Okay, that is equal to 3.2 ohm. Then this 2 ohm resistance, then B 2 ohm, C, and finally this is B dash, and here is the R equivalent. Then what about this 3 ohm, 3.3 and 2? They are parallel to each other. So let us replace it with their equivalent resistance, 3.3 parallel to. So that will be equal to 1.23 ohms. Okay, this equivalent of these two resistances, then followed by B, then 2 ohm resistance, here C and B dash are equivalent. Then these 1.2 ohm and 1.23 ohm and 2 ohm resistance are in series. So let us replace it with their equivalent 1.23 in series, that is C and B dash. That will be our equivalent resistance in this case, that is equal to 3.23 ohm. Okay, now the equivalent resistance we obtained is equal to R equivalent is equal to 3.23 ohm. Okay. So let us find the total current supplied by this voltage source IT. Therefore IT will be V by R equivalent is equal to 20 by 3.23. Okay, R equivalent is 23. That is equal to 6.19 ampere. Okay, right. Can write the I total. Here we obtained it as 6.19 ampere. Okay, 6.19 ampere. That is going to split into two, I2 and I1. So let us find I2 first. Okay, for that purpose, I'm going to draw the circuit to the left of this node. So to the left of BB dash. Okay. Here we obtained I total. So to find I2 and I1, I'm going to redraw the circuit for this portion only. Here it is I total, and the magnitude of the current is 6.19 ampere, and this is 2 ohm resistance, and here we have a 2 ohm resistance that is written over here, and 3 ohm resistance, and finally 2 ohm and a dash. Okay, right. So our next aim is to find the current I2. For that purpose, we can apply the current division rule. This total current IT is going to split into two components, I1 and I2. So in order to find I2, we have to apply the current division rule. So let us replace the 2 ohm resistance and 3 ohm resistance using its equivalent resistance. Okay. Okay, here it is current I2, and these 2 ohm and 3 ohm are parallel to each other. So I'm going to replace these two resistances with a single resistance as 2 into 3 ohm divided by 2 plus 3. Okay, and then this is our 2 ohm resistance, and here we have a 2 ohm resistance once again. Okay, this is I1 and this is I2. Okay, right. And the result I am getting is 1.2 ohm, and this 1.2. Okay, now let us apply the current division rule. I2 will be I total into I2 is the current flowing through this branch. Okay, so we have to consider the resistance in the opposite branch, that is 2 ohm. Okay, this 2 ohm resistance and 1.2 ohm resistance, that is common, that is common for the current I2. Sorry, resistance opposite to the current I2 is 2 ohm divided by total resistance in this loop is this 2 ohm plus this 1.2 ohm plus this 2. Okay, that will be I2. Here we have I total is equal to 6.19. 6.19 into 2 divided by 5.2. That will be the current IT. The I2 is equal to 2.38. Okay. So let us mark here it as 2.38. Again, this 2.38 is going to split into two components. This is I and this is I3. Okay. Again, to find our role is to find the current I. Okay. We know the magnitude of current I2, that is equal to 2.38. To find the current I, let us apply the current division rule as I is equal to, what is the total current coming to this node, that is I2. Simply that is I2 into Okay, the resistance opposite to the flow of this current I is this 3 ohm resistance. Then 3 ohm divided by total resistance in this loop, that is equal to 2 ohm plus 3 ohm. That is 2 plus 3. What is I2 here? That we obtained it as 2.38 into 3 divided by 5. That is equal to 1.43 ampere. And now uh, let us back to this circuit. Now we had to take the ratio V by I. Okay, here we obtained, here we have the voltage source, and now we got the current I. In this case, current I is equal to 1.43 ampere. So in the previous case, we found the ratio between V by I. In case 2 also, we have to evaluate the V by I ratio. Okay, is equal to V is equal to 20, and I here it is for 3, that is equal to 13.99. Mark it as equation number 2. On comparing equations 1 and 2, now compare the equations 1 and 2. Okay, by equation 1, the V by I ratio is 13.9, and by equation 2 also V by I ratio is 13.99. Then we can say that equation 1 is equal to equation 2. Hence, we verified the reciprocity theorem. Okay.